Okay, so we're embarking on this path of looking at the implicit regularization of gradient methods. This is the kind of high-level agenda. And by this, we mean properties of the solutions to which these methods converge. And we're taking a little detour to review, today at least, some ideas from optimization theory. And we'll meet just a few of the tools that'll be useful there in understanding properties of gradient methods and the solutions that they find. Okay, so let's. So one of the in constrained optimization, you know, we're concerned with the nature of the solutions. We saw last time I put up there this theorem about local minima. You know, that necessarily a local minimum is a stationary point, and in the convex case, this is sufficient for it to be a global minimum. We'll see the corresponding result in the constrained case. We need to be careful about what the constraint sets look like. So let's have a few definitions. So first of all, a tangent direction to a set. So V, we're always working in RD. So V is a tangent direction. And our set we'll write as X at a point in that set. If we have sequences, x1, x2, blah, 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 and let's say delta 1, delta 2, blah, blah, blah. So these are I guess all of these are in our set. These deltas are real numbers, such that the deltas are decreasing to 0. And I better write this the right way. V is the limit of these points xk minus x divided by delta k as k goes to infinity. All right, so you know, we've got, let's draw a picture up here. We've got our set X. This is X, and this is our point X. What did I call it? Just little x, right? And then the set of tangent directions here, you know, are all of the directions that we can reach. So they're kind of everything out here. The tangent cone. Okay, we'll revise our picture in a moment. The tangent cone at x, tangent cone 2x at little x is the set of these tangent directions. V is a tangent direction. Tangent direction 2x at 2x at x. All right, so up here, our tangent cone, maybe we can use some colors. You know, the luxury of colored chalk here. Our tangent cone is going to be this set. All right, everything going off here. This is T x at that x. And I guess, you know, a cone has this, you know, all positive expansions are included. So for every x in a, so a set is a cone if for every point in that set, and every positive alpha, alpha times that point is also in the set. So the tangent, so this is a cone, and the polar cone of, I'm going to say a cone C, C in RD is this convex closed cone. We write C polar. We've got a little blemish on the board here. There's no significance to this dot. Is the set of directions where the inner products are non-positive. Okay, so in this case, we can use another color. In this case, of course, you know, to be non-positive with some direction up here, we're looking like this, and with some direction here, we're looking at that, and we need to be in the intersection of all of those half spaces. So our polar cone here looks like this. Right, the polar cone of our tangent cone is this yellow region.
What is the exponent to C?
I'm sorry?
The exponent to C.
So this is the symbol for polar, right? You know, somehow this is standard with a little circle in the exponent. Yeah. So I know you're not a LaTeX fan, but in LaTeX it's
Yeah, but everything is fine.
good. It's superscript /circ. Yeah.
If the delta are negative, can the cone go in the other direction?
If the delta are negative, can the cone go in the other direction? Good point. I guess I omitted an R+. They're decreasing to 0 here, right? So these are all positive. Yeah, thank you. So absolutely not, yeah. All right. So, you know, of course, this is an intersection of a bunch of half spaces, right? So it's a convex set and clearly a cone. Okay, and so these things, you know, so last time I wrote this theorem that if so suppose f is differentiable at x in Rd if x star is a local min of f in Rd maybe I'll put it over here. Then grad f is 0, and it's an if and only if f is convex, and grad f is 0. Then x star is a global min. In Rd, we use our coloured chalk again. Okay, but when we're in the constrained case, considering a point, I guess that was an x star. right? In the constrained case, when we're talking about f being differentiable at some point, if this is a point in X and it's a local min, if this is a local min of f in X, then instead of the gradient being 0, we get, the negative gradient at X star is in the polar of the tangent cone at X star. I'll write it this way. Okay, so the picture to have in your head is where we want to decrease f. We want to find a minimum of f, but the only directions in which we can go to decrease f lie in this polar of the tangent cone. Okay, so this is the corresponding condition in the constrained case. And if it's convex and this condition is true, then X star is a global minimizer of, actually there's an extra condition. F is convex and the set X is convex. Then this is a necessary and sufficient condition for a minimizer, and it's a global minimizer. Okay, so this is conceptually very simple, and these polar cones, very, very nice. But we're going to consider a simpler family of constraints of these kind of constraint sets, for which we can be a little more explicit about the nature of the polar cone, right? And we'll see all the examples we'll see are actually, not as general as these kind of crazy shapes I'm drawing up here. And I'm kind of sweeping under the rug a bunch of case-by-case stuff that arises in optimization theory. I'm gonna present as a definition the kind of family of constraint qualification conditions that people use that are sort of sufficient conditions for getting the tangent cone in a nice simple form. Okay, so we'll work with a specific family. I might actually write it up on this board. A specific family of constraint sets. So in particular, things that are defined in terms of equalities and inequalities for differentiable functions. Okay, so let's call this the canonical constrained optimization problem. And it's just min of some function f such that gi of x is less than or equal to 0, and there are going to be, let's say, n of these inequalities, and hi is equal to 0, and there are m of these equalities. Okay, so this is the kind of family of constraint sets that we're going to define. We're going to think about, all right, let me erase this. Any questions about definitions? Feel comfortable? So with this definition, that's our set X, our constraint set. It's the set of points that have, so X here is these guys that have gi x less than or equal to 0 for I going from 1 to n, and hi x equal to 0. points that lie in X we say are primal feasible. And I'm just writing that, yeah.
So the indexes are the same?
If you don't like using the variable twice, we could call this one J. Yeah.
So in the definition, borrow the I2.
Yeah. So okay. So for I going from 1 to m, yeah. All right. So for all I in n and j in 1 to m. Yeah. Okay, and I'm writing this up in case I say it. This is, standard terminology for a primal feasible X. The set of active constraints. So the inequalities are kind of the interesting ones. The set of active constraints here, and it's written I0 for a point X. These are the indices for the inequalities where that constraint is active, right? Which means gi of x is equal to 0. So we have no slack, no freedom. We're right at the boundary. And we're going to say that, so this is kind of a definition that I'm using to avoid a lot of detail that is really just going to save us some time. So we say that X satisfies the constraint qualification conditions if so we'll use this as shorthand. So for all active constraints, GI is differentiable at X. And for all indices of the equality constraints, HI is differentiable at X. And the tangent space at X is the set for which the set of directions where the gradient of GI in that direction is non-positive for active constraints, and the gradient in all of the equality constraint, the gradient of all of the functions defining these equality constraints is 0 for all m of those. So when we have, this is a simplification of our tangent cone. I'm actually to some extent oversimplifying. We don't need to work with differentiability. We'll see a bit later on cases where we get around that. We can work with subgradients. This form of the tangent cone is true when the functions gi and hi satisfy particular conditions, and there's sort of a family of those that are in some sense incomparable. So I'm kind of sweeping all of that under the rug and saying, for the problems that we consider, we'll always be in this situation of satisfying these conditions, and in that case, the tangent cone has this explicit form. Just to give you an example of one of those, there's a Slater's condition which says, if you can find a point x in the constraint set for which all of the gi's are less than 0, then in the differentiable case, then this suffices, right, to be able to write the tangent cone in this way. So it's really just to write that inclusion in the polar of the tangent cone condition as something really rather simple and intuitive. Okay, and
that has to be an equality or could be an inclusion?
It's an equality, yeah. And when we're in this situation of satisfying the constraint qualification conditions, then we can define these explicit conditions called the Karush-Kuhn-Tucker conditions. And let me see, I'm just trying to calculate if I can write another theorem with some with a third color, but I don't think I can. So, okay, so let's write out the KKT conditions. In fact, I'll do that over here. So for the canonical constrained optimization problem, the Karush-Kuhn-Tucker conditions. Now these are conditions not just for an x in our constraint set x, that the set of points that satisfy these equalities and inequalities, but we also have dual variables, alpha 1 to alpha n. You can think of as Lagrange multipliers. The alphas are greater than or equal to 0. The dual variables for the equality constraints are just real numbers. And the two conditions, it's problematic to see down this low, isn't it? So I'm going to squeeze this up a bit. Alpha 1 to alpha n greater than or equal to 0, beta 1 to beta m in R. And our conditions are the Karush-Kuhn for that, grad f x. I can fit it. Plus the sum of the alpha I grad g I x grad h I x is 0, and the second condition is alpha I gi of x equals 0 for I equals 1 to n. Okay, so this is a explicit statement of the negative gradient of f lying in the polar of the tangent cone in that first line. The second statement, the alpha I gi of x equal to 0, is called complementary slackness. Maybe I'll write that down. And it's complementary slackness means, you know, you're requiring that you can have slackness in the GI constraint, so the GIs can be strictly less than 0. You can have slackness in the alpha constraint, they're allowed to be strictly greater than 0, but you can't have both at once. Okay, and then these are necessary conditions for a local minimum. So I'm going to write something like this theorem again, but replacing this this expression for the tangent, the containment in the tangent, the polar of the tangent cone, explicitly in terms of those conditions. So we have for this canonical constrained optimization problem, let's call it CCO. For CCO, 1 if x star in X is a local min of F, local min in X. I guess I should be explicit. And X star satisfies the constraint qualification condition. Then there exist dual variables, so alpha 1 to alpha n greater than or equal to 0, and beta 1 to beta m in R, satisfying the KKT conditions. So these, we'll call this KKT. Great, and if F is convex, if the G1 to Gn are convex, if H1 to Hm are affine, and X star satisfies the constraint qualification condition. Okay. Blah, 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 that happens. X star satisfies the constraint, and there are, and for and some alpha and beta and let's say with some alpha and beta, blah, 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 satisfies KKT. Then X star is a global optimum. In X. Global optimum of F. Okay, so in the elegant case where F is convex, where the constraints on G and H, these conditions on G and H imply that the constraint set X is convex, then these KKT conditions are necessary and sufficient for optimality. But quite generally, they're a necessary condition for optimality. A necessary condition for local optimality. But these are just first order conditions, so it's important to realize they're necessary, but not even, they're certainly not sufficient even for local optimality, because we're really just talking about, a stationary point. It doesn't need to be a local minimum. Okay.
So in the point 2, you need X convex.
You need what?
X convex or not?
For point 2, we need X convex, and that's the G1 to Gn convex and H1 to Hm affine implies that the set X, the constraint set, defined by, right, so if G is convex, if Gi is convex, then the set Gi less than or equal to 0 is a convex set. And if Hi is affine, then we're in good shape for the equality constraints as well. So yeah, this condition implies that our constraint set X is convex. Together with F being convex, then this local condition is a global one. And it's also sufficient for optimality. Okay, so we're going to be, using these ideas. I'm not going to go through proofs of any of these sort of results we're recalling from optimization theory. You can convince yourself in any of the special cases actually that we're looking at least for the next lecture or so, that the polar of the tangent cone has exactly the form that we're describing, because the sets there are pretty simple. But I wanted to use this general kind of formulation of these problems as canonical constraint optimization problems, and this nice formulation of the necessary conditions for local optimality, these KKT conditions. Okay, so let's go back to a very simple application of these. We saw a theorem last time, and we went through an argument to understand the role that the sample covariance matrix played there, looking at linear regression in an overparametrized setting and a gradient approach for solving that least squares problem. And we saw that the solution that a gradient method converged to was the minimum norm, let's say interpolating solution in the case where the initialization was 0, and we have a full rank data matrix, so rank n data matrix. Okay, so we're going to look at as a very simple application of this sort of terminology, we're going to look at a slight generalization of that result, and we'll see, it's really an easy consequence of these ideas. So let's go let's consider, okay, all right, this is theorem for, so we're going to consider an empirical risk. It's in a slightly different form, and I'm really saving some writing to put it this way. The empirical risk we'll look at is the expectation under the empirical distribution of, and we'll write these losses as L sub yi, so in general a different loss for each outcome of xi transpose theta. All right, so in the case we were considering before, this function was yi minus xi transpose theta squared. I'm writing it that way to be a little economical. Where the loss, where L satisfies for all y, considering real outcomes here, the derivative of the loss at, let's say, for all y in R, and for all y1 hat, y2 hat, and so on, all sequences. The derivative of the loss at y hat k approaching 0 implies y hat k approaches y. Certainly true for our quadratic loss. And then the kind of condition we had before was our initialization of our gradient method was at 0. Our data matrix, right, the matrix with all of these rows, these n rows xi, has rank n. If gradient descent converges, then it converges to the solution to the min norm optimization, min norm interpolation problem. Sorry, write that out. Min of Euclidean norm of the parameter vector such that x theta equals y. All right, this was the optimization problem that we saw previously. Okay, so let's go and just as a an application of these tools, let's see why that's true. Okay, so we're going to work with, we have our okay, so let's think about this optimization problem. It's certainly in that form, right? F is the, so the x over here is theta. F is the this quadratic function. We don't have any g's, so n is 0. We only have the equality constraints. and these equality constraints, the functions h are affine in this case. So we have affine and convex, and that's nice. Our KKT conditions are necessary and sufficient for a global optimum of this problem. So, you know, the primal feasibility condition, primal feasible, the condition for lying in the constraint set is x theta equals y, and I should be writing vectors here. This is our data, x and y. And then, you know, what are the HIs? They're this, each one is xi transpose theta minus yi. That's the, we have n of those. So I guess our indices are a little different. Grad f in this case is just theta. So, you know, when we write out the KKT conditions, grad f plus the sum of beta I times grad hi equals 0, that's just grad f is theta, the sum of the beta times the grad h term is x transpose beta, and we want that thing to be equal to 0. All right, so those are our KKT conditions. Theta needs to be negative x transpose beta. And you remember gradient descent was theta t was theta t minus 1 minus a step size times the gradient of the empirical risk. So we can write the gradient descent update as theta t minus 1 minus, and I want to write it in the form of x transpose r t minus 1, where we're writing this vector r RTI is defined as the step size times the derivative. We've got our negative in there. The derivative of L at, I guess we need yi for the ith component, and it's xi transpose theta, maybe theta t. Okay, so this is our gradient update, and we'll write it in that form, and you know, this clearly folds up, and we can write the whole thing. When we start out at theta 0 equals 0, we can write the whole thing as negative x transpose a sum of these r's. Okay, so and then you can see, you know, this condition on the gradients. Okay, so if gradient descent converges to theta, to some vector theta, question?
I'm just wondering, is it L of theta t or theta t minus 1?
So I wrote RT here for theta t, and that is theta t minus 1. Yeah, so maybe this would have been a little clearer.
Oh, sorry.
No worries. That's good. I'm sorry. That's the derivative of this loss with respect to its argument. You know, why I wrote loss as a function of one variable, so I can, yeah, sure. As a function of its scalar variable.
The second to last line, you have RT minus 1.
Yes.
Where RT minus 1 cover I.
This is the ith component of this n vector, yeah. Yeah, so RT minus 1 is in R is in Rn. right? There are n components, and the ith component is concerned with the ith xy pair. Yeah. Okay, so we know that our data matrix X has rank n. So, so this linear mapping from Rn to Rd is 1 to 1, right? So, so if and we're just using as a hypothesis that gradient descent converges. Certainly for small enough step size, this is easy to prove, but if it converges, if gradient descent converges to, let's say, theta, then because it's rank n and a 1-to-1 mapping here, then theta t then this thing, so negative x transpose that stuff approaching theta, implies there's a unique beta in Rn such that negative x transpose beta is the thing that we're approaching, such that negative and that's what we're converging to. So this sum from 0 to t minus 1 of Rs approaches beta.
So today you changed the notation for lowercase a.
For lowercase?
Yesterday you defined lowercase a has 2 arguments, and the first one is...
Oh, that L, yes, absolutely, yeah. So yesterday I wrote this as L.
Second argument is written.
That's right. I wrote this yesterday as L of y hat y. Maybe this is just confusing. I was saving myself some effort because I didn't want to have to write the derivative with respect to the first argument of this, yeah? Or come up with some notation for that. So I just wrote this as that because I'm only concerned with the derivative with respect to this scalar argument. Yeah. Yeah. Why are we taking... Oh, okay, so if let's compute, so what are we minimizing here? It's this empirical risk. And so the gradient with respect to this thing, right, is 1 over n, the sum of L prime of this thing times xi. Okay, so the xi comes from the derivative with respect to theta in here. Is it because I think I've missed a 1 over n here somehow? Is that right? I have. Yeah, this should be like this. Was this the issue? Thank you. That was the problem? Yeah, okay, thanks. Okay, so so we have this sum of RS's approaching beta, so the this vector RS must certainly approach 0. So, you know, that tells us that these derivatives for the theta, the sequence of theta, these derivatives are approaching 0 separately for each yi, and our condition here is that that must mean that our xi transpose theta is approaching yi, right? So hence, I'll write it just in matrix form, x transpose theta, theta t converges to this vector y. Okay, so, x theta equals y. This is satisfied by that limiting point. Negative x transpose beta equals theta. The other condition is satisfied by that negative point. And we don't have complementary slackness because we don't have any inequalities. So we satisfy the KKT conditions with that beta, those dual variables beta and the limit of theta, whatever this gradient descent algorithm converges to. And again, because we're in the nice convex criterion, convex constraint set, the KKT conditions are both necessary and sufficient for global optimality. So we're finding a solution to this optimization problem.
I'm a bit confused. So it seems that x theta is in the image of xt, but then
yes.
You apply xt to theta. So
I shouldn't be applying xt to. Oh, thank you. Okay, so this is x theta. Thank you. This is a typo. Good. Yeah. Right, and what I'm looking at, I wrote the transpose because I was looking at each of the rows of x here, right? But x contains these rows of x. So, yeah. Yep.
So the final theta is the minimizer of the L2 norm or the empirical risk?
It's a minimizer of this empirical risk.
Okay.
Yeah. So this, I'm sorry, actually all we're saying here is under these conditions, this thing is going to, the derivative is going to 0, and the theta that we approach is a global optimum of this constraint optimization problem. So it's the minimizer of this norm subject to the interpolation condition. Yeah. But, expressed in this way, all we're saying is stationary point implies that we're approaching this outcome variable. Yeah. Okay, great. Okay, and something else to notice, all we're really exploiting here is that we're staying in, the crucial point was we were staying in the span of the data here, right? So we're in in our d-dimensional space, we're in an n-dimensional subspace, affine subspace. So, and in particular, the parameters are always staying in the span of the gradient of the empirical risk. So any method that does that makes updates that leave you in that span, we can say exactly the same thing about the points that it converges to. So that includes, this was gradient descent, but of course we could make essentially an identical argument for gradient flow, and actually much more complicated things. So if you're working with momentum methods, Nesterov acceleration, these are these kind of second order time discretizations of second order differential equations. They involve a kind of linear dynamics with some memory of past gradient updates. But again, that's just linear in the sequence of gradients that you measure along the way. So when we're staying in the span of those of that sequence of gradients, then again, we're constrained. We're going to arrive at the same sort of conclusion where the optimum. And I guess the other crucial point is those algorithms don't change the stationary point. They're just changing the path by which you reach the stationary point. So in particular, the solutions that they find in the over-parametrized case are always going to be minimizers of the norm subject to the interpolation constraint. Okay, so it's a much more general phenomenon. So this theorem is going to motivate stuff that we'll look at later. When we look at benign overfitting, one of the examples there is going to be linear regression in the overparametrized setting, where gradient methods converge to the minimum norm interpolant, and so that's the estimator that we'll consider in that setting, and we'll look at its statistical properties. Yeah.
I'm slightly confused how we get as a conclusion that essentially, I'm guessing it's x theta equals y, right? This is sort of the result of that.
Yes, that's right. So if gradient descent converges to this theta, since x is rank n, that linear map x transpose from the sum to the this quantity is a one-to-one map, and so there's a unique element of Rn that gives us this for whatever gradient descent converges to.
This is KKT.
I'm sorry?
This is KKT, right?
This is the KKT condition. That's right. Yeah. So this tells us that we satisfy the KKT conditions, and then we can go ahead and verify that actually theta, the theta to which gradient descent converges, is feasible. Yeah. So we've got a feasible point and a beta with our KKT condition satisfied. All good? Yeah. Okay. Let's look at a bit more of a, what are we at? 9:10, we have half an hour. Good. Let's look at another example. This one is this one is looking at logistic loss. So moving away from so something that we relied on here was that the optimum is finite. Okay, so when we're thinking about a quadratic loss, we're always going to be in that sort of situation. So things change, but apart from that, it's a pretty general condition here, right? We're just interested in stationary points having this sort of interpolant. For logistic loss in an overparametrized setting, things are a bit different because we may generically we should expect to find a solution at infinity, right? So we're going to be able to drive a logistic loss to zero, but there are lots of different directions in which, typically anyway, there are lots of different directions in which the logistic loss can go to zero, and which one would a gradient method find? Okay, so we're gonna look at that next. Okay, what's the? Yeah, maybe we'll start from here. Okay, so we're looking at the case of a linear classifier with, so we're going to use the same notation for our data. X is x1 to xn as row vectors. Y is now a plus or minus 1 vector. And we're working with linear classifiers. So let's look at the empirical risk with logistic loss. So we write L hat. I'm just using the same, overusing this notation. And for now, we've I guess generally it's L. We're back to L, but now we're going to make it a single argument by looking at the product of yi with our f of xi, our linear function. Our f of xi here is just xi transpose theta. Okay, so in the logistic case, flipping the sign is enough. So that's okay, so I'm actually going to step away from the logistic loss, which remember was this log 1 plus e to the minus this thing. Maybe I'll write this out explicitly. Y hat y. Right, that was our logistic loss. Now, when we're on the wrong side of 0, when we have a negative sign there, then that thing grows linearly. Okay, which is nice to have that Lipschitz property, and we'll see it pop up later. On the other hand, when we're on the right side of 0, we have an exponential tail. We're going to make our life easier and just look at exponential loss because we're just considering what happens at infinity. You can make things precise and give a result for logistic loss by arguing about how close this is to the exponential in some multiplicative sense, and it's all good, but we can actually make our life a lot easier just proving the theorem for exponential loss. So let's do that. So let's work with that. So this L is just e to the minus, right? LA is e to the minus a. All right, so it's exactly exactly this. Another wrinkle that is not too hard to get around, but it just complicates things, is working with a kind of any data that's strictly linearly separable. But I'm going to again take a shortcut and say for almost all x, all right, so for all but a set of measure 0, and all y, for which the data is strictly linearly separable, all right, so such that what do I want? Let's say strictly linearly separable, and I'll write it separately. Strictly linearly separable gradient flow satisfies theta t equals theta star log t plus n plus a remainder term where, okay, rho t is uniformly bounded. As a function of time, and theta star is the is the max margin vector let's say, which solves the optimization problem min over theta in RD. I'll write it as a half theta squared for Euclidean norm, such that the yi xi transpose theta is at least 1 for I equals 1 to n. And since this thing is uniformly bounded, that tells us that, as t goes to infinity, this theta t direction approaches the theta star direction. Okay, and I said strictly linearly separable. What that means is that you have a strict inequality in, this set of inequalities can be achieved by some theta, right? Okay, questions about the theorem statement? Clear? So we'll work with gradient flow. We can get this nice explicit expression. You can make a similar conclusion for gradient descent. Yeah.
Is this what people call SVMs?
That's exactly right. So this is called, all right, so let's look at why it's called a max margin vector, but this is exactly the optimization problem that arises in support vector machines. Yeah. Okay, so yeah, let's think about this optimization problem. It arises in SVMs. It's called max margin because if it's feasible, which we've assumed here and in the overparametrized case is a generic.
Sorry, no.
Yeah. Okay.
We use the loss function. Where is the loss function of here?
The loss function is this exponential function.
Yeah.
And we're using that because we're running gradient flow, right? So gradient flow is the differential equation. It looks like this. Yeah, so that's true. Anything else I should be reminding you of? I don't think so. All right, so yeah, let's think about this this max margin optimization problem. So if it's feasible, so if there's a feasible point, then it's equivalent to max over V and gamma. So maximizing the margin subject to yi xi transpose theta is at least gamma for all I. And we're going to consider normalized V. Okay, and in that case, you know, if we take the solution theta star over there as, you know, V star over gamma, we get the greater than or equal to 1 inequality satisfied. So we just need to scale this solution to get our minimum norm separation thing here. And then this thing, you know, V is a direction in RD. So our unit vector defines a linear classifier. And we're trying to choose the direction so that, you know, if our data looks like something like this, you know, these are the negatives, and these are the positives, then, you know, that's the direction that gives us the maximum gamma, and for a unit vector, gamma here is how far we are, how far the closest point is to the decision boundary. So we're adjusting the direction to maximize that distance to the decision boundary. So yeah, this is exactly what arises.
Again, there is theta. It should be a theta.
Oh, I'm sorry. That should be a V. I'm standing too close to it. Thank you. Okay, so, you know, and clearly this is in the form of the canonical constrained optimization problem, right? The GIs are gamma minus this quantity that we want to be less than or equal to 0. The F is, or actually this one, let's think about this one. 1 minus this quantity we want to be less than or equal to 0. F is our nice quadratic. So the KKT conditions for this optimization problem, the max margin one as I've written it on the left, right, are going to be so for a theta in RD, and we need n dual variables that we called alpha in non-negative alphas, and we're going to have grad f is just theta. F here is a half norm theta squared. Grad gi is the gradient with respect to theta of 1 minus this thing, so that's going to be a yi xi. So this sum being equal to 0 is going to give theta equals the sum of alpha I yi xi across our data. And the complementary slackness condition is alpha I times 1 minus the g here is yi xi transpose theta. That thing is equal to 0. Okay, so what this tells us is that we can write the solution to this optimization problem as a positive combination of the xi's appropriately flipped, right? We flip the ones with a negative label, you know, reflect them through the origin. But these alpha i's are necessarily 0 if we have some slack here, right? So I'm annoyed I erased the picture. So the points that are actually, you know, support vectors, the ones that are at distance, that satisfy this inequality as an equality, those points can have a positive value of alpha, but all the other points have a 0 value of alpha. All right, so we can write the solution as a sum of just the subset of the data that corresponds to the active constraints, the I0 for that optimal theta. Okay, so and you know, in the context of support vector machines, this is where the name support vectors comes from. All right, so we're going to have time to get a little bit of intuition for the proof, but I don't think I can go through it at a decent pace. So let's do that. Let's think about what you know, why we should see something of this form. I think I want to leave everything up, so I don't have much space. So okay, let's erase this. All right, I might try and leave the KKT conditions up there as well, so I'm probably going to wave my hands. Okay, so if we think about, you know, what gradient flow is going to do with this loss function, so, you know, we've got theta t. Let's say it approaches some limiting direction. So maybe I should write it as theta t over its norm. If that converges to a direction theta infinity, maybe better, let's say theta t. If theta t approaches some direction theta infinity, then maybe we've got some function phi of t times theta infinity plus, you know, some other little residual fluctuations, right? That's, this is something that's dominated by this, right? This is a vector, this is a scalar, but the magnitude of this goes to infinity, where this one, let's say, is bounded. Then, you know, we can write the descent direction for gradient flow for our theta, the theta that's converging in direction. We can write that as 1 over n, sum across the data of, so L hat here is e to the minus yi xi transpose theta. The negative direction takes care of the e to the minus. We get a minus yi xi transpose theta times xi. And you know, we can plug in that should be a theta of t. And if theta of t has this form, then we're getting this, you know, sum of an exponential with a couple of pieces, so a product of two terms, e to the minus phi of t times yi xi transpose theta infinity times an e to the minus yi xi transpose times this residual rho t times xi. Can you all see that? Is that good? Oh, good. Okay. Okay. So you know, this is a quantity that's going to infinity. So you know, that's going to drive everything down to 0. But we have that quantity going to infinity multiplied by these kind of margin terms, yi times xi transpose theta infinity. So the sum's going to get dominated by the smallest values of these. Yeah.
So why is yt going to infinity?
So we're thinking of the case where our data is strictly linearly separable, right? So there is a direction where we can get everything classified correctly. If we have such a direction, then we can drive this e to the minus loss to 0 by going off to infinity in that direction, There's a whole set of those directions, but you know, we should expect in the case where it's linearly separable, we should expect to go to infinity in a direction that gets has our exponential going to 0, right? So you know, here I'm saying let's suppose, and this is sort of some intuition behind why we prove theta star times log t plus n as the dominant term here. You know, and we're going to just write that down as a starting point and then prove that's the form of this theta t, and I'm justifying that starting point at the moment in a hand-wavy way. Yeah. So you know, we know that we should expect this to go to infinity if it converges in direction to theta infinity. Then it's going to have a form, you know, something that's going to infinity times that direction plus some other thing that's dominated, some other vector, you know, error term that's dominated by the scale of phi t. Okay, so then we get something, there's this multiplicative thing over here where we're taking a combination of the x's. Did I drop some y's from this? I think I did. Right? I should surely have a yi everywhere, right? So this is a yi xi. Okay, so you know, this is an e to the minus something going to infinity. The different data points have different multipliers here. You know, because it's an exponential, the ones that are going to dominate are the ones that are closest to 0, so the smallest in value. And you know, of course, that means the parameter vector is moving in the direction of those points, those xi, yi products, the ones that are dominating this weighted sum. And so we should expect it to move towards a positive linear combination of the yi xi's that have the smallest value of the margin. You know, that if we think of the expression, you know, okay, the ones that in this setting have this quantity equal to 1 versus, you know, strictly larger than 1. Okay, so we expect to see theta infinity in the theta star direction, right, in the solution to this optimization problem. And if we were to scale theta infinity so that, you know, the margin for the smallest points is exactly 1, then, you know, then that theta infinity should be precisely theta star. And in that case, you know, so we expect I'm just going to write theta infinity equal to theta star. That involves some rescaling. That's fine, just rescaling by a constant. You know, whatever that smallest margin was for our theta infinity, let's rescale it so that the smallest margin is 1. We expect that, and we also expect that, you know, theta dot t is going to be something like the derivative of phi, certainly dominated by this, times theta infinity. And we want that to be, you know, the negative gradient as a function of time, which from this expression we see is, you know, something like, I guess I should write proportional to. I don't know how to write approximately proportional to. E to the minus phi t. Okay, so this is a big clue that we should be looking for logarithmic growth in the phi in this phi function, which is, you know, what we see in the theorem statement. So that's going to be how we start our proof. Yeah. Okay. I think in the 4 minutes remaining, I'm not going to do anything useful. So, any questions? All right, good. Thank you.